Okay, good morning. So let us continue the lesson. So if you remember, we talked about Euler's theorem. At that time, I was not completely sure that if the theorem was correct for also multigraphs, but we learned, yes, I checked it again, so that's also correct for the multigraph as the previous example showed. So what was the theorems? What is the Euler's theorem? Let G be a connected simple or multi-graph, it doesn't matter, with P vertices, Q edges, and R regions. So do you know what's the meaning of region? Yes. So if you have a planar graph, you can draw it in a way that the intersection only happens at vertices. If it is a planar graph, and the number of R denotes the number of regions in that case. So I don't want to prove it formally, but at least I wanted to give you some understanding of why this formula might be correct. So the number of vertices minus the number of edges plus the number of regions is equal to 2 if you have, oh, it's a very, very important thing that I have missed here. Yes, because the notion of region doesn't make sense if the graph is not planar in the first place. So that is the most important part. So I don't know. I have forgotten to write it down. So a connected planar. So let me just add this part, which is very important here, actually. Otherwise, it doesn't make sense at all to talk about regions in the first place. Okay. Now, let us consider only if as I told you, that I don't want to prove it actually very formally. It is not included in the book, but let us understand why might this formula be correct in the first place. If you have a planar simple graph with P vertices, Q edges, and R regions. So assume that you have a graph, even though it might look complicated, but if you want to start drawing it, you start with putting points and drawing edges and then adding edges to the uh, previous picture, and then you make it more complete toward a complete picture of the graph. Yes. So if I give you let us repeat this. I give you a planar simple graph with P vertices, Q edges, and R regions, and I ask you to draw it. You put the picture of the graph in front of you, and if you want to start drawing it, you start from somewhere. Yes, you put a point, and then you add one edge, and then look at the picture, and then pick up another point and add another edge and something like that. Yes, this is the way that you start drawing the graph. Yes, but let us see what happens. For example, let us start with this scenario. So this is just an informal way of proving it. For example, you see the picture, you put this point, and then you see that in my picture there is another point, and then you see that there is a connection between them. So this is what you just draw, yes? And then what happens here? And you start completing your graph. For example, in this simple case, what is P here in this case? Is 2, yes? What is Q in this case? It is 1. And what is R in this case? What is R in this case? The number of regions? It's 1 again. And then you calculate P minus Q plus R. So what would be the answer? The answer would be 2 minus 1 plus 1, which is exactly 2. So for this one, it's completely correct. So the real proof of that is mathematical induction on the number of edges, but because you also want to prove it for multi-graph, you need to be a little bit more careful. But the idea is very similar to what I'm trying to say. Okay, and then be careful. There is a connection here that the graph should be connected. So, and then I look at my picture once again. So I realize, for example, that this might be connected to another one. Yes. And what is happening here? If I add this one, let us see how P is changing. So can you tell me what is P happening? P goes to P plus 1 because now the number of vertices increases by 1. Yes? What happens for Q? Q goes to Q plus 1. Do you agree? Because I'm adding one edge. And what do you think about the number of regions? It's the same. So you see, this one and that one will cancel each other because it's still P plus 1 minus Q. So you see, let me calculate. P plus 1 minus Q plus 1 plus R is again same 2, yes? because this one that is added here and that one are canceled, and I go back to P minus Q plus R. So it means that if I add one edge, of course the number of vertices is changed, the number of edges also changes, but in this case the number of regions remain the same. So this plus one coming from here and that plus one coming from here in the Euler's formula will cancel each other because one of them is positive, the other one is negative. Yes? Is that clear? Okay, now let us do one more thing. What might be the scenario here? It might happen that I still go from this to another one, or it might happen that I connect these two. Okay, so let us see what happens. For example, if I have to connect these two, I look at the picture. In the picture, I see that these two are connected. So what's happening now? So if I add this one, let us check again. What is happening to P? P is the same P. Do you agree? Because in this scenario that I am connecting to already their vertices, then I am not adding anything to vertices. So P is just remains fixed. But what happens for Q? Q becomes Q plus 1. But what happens for R in this case? R plus 1. Yes, it increases by 1. Now this time, again, this plus 1 here and this one cancel each other. Again, I will have the same scenario that the number of vertices minus the number of edges plus the number of regions is still the same. And then let us see, for example, what happens. If I do something like that, what is the next choice? The next choice is probably to put a leaf here. When I do this, so in principle, you see that whenever you want to start completing your graph, when you add an edge, this edge might be connecting to a leaf or might be making a cycle for you. If it is making a cycle for you, then what happens? The number of vertices is not changed. The number of edges is increased by 1. And because now you are making an extra cycle, the number of regions also grows by 1. So they cancel out. Yes, because one of them appears with negative sign in the Euler's formula and the other one appears with positive sign. Yes, or you might have this scenario that you just connected, I don't know, to a leaf. Yes, in that case, what happens? You are increasing the number of vertices by 1. You are increasing the number of edges by 1, but you are not affecting the number of regions. Yes, is that clear? So then it means that again you go back to the same. So if you start from a graph for which P minus Q plus R is equal to 2, if you start completing it, you will not change this number because there are only two possibilities. Either you add one edge with a leaf on that, it means that you are increasing P 1 unit, you are increasing Q 1 unit, but you are not affecting R at all. So it means that in general, the answer is again 2 because it was 2, it remains 2. But now if I have this scenario, what is happening? I am increasing the number of edges by 1 unit. I am not affecting the number of vertices, but I'm also adding the regions number 1. So if I start from a graph for which P minus Q plus R is 2, by by completing my graph, this number will remain invariant. It will not change. So even though it seems a very hard theorem, it is not that theorem. Yes, it's understandable immediately. Is that clear? Yes or no? Okay, so this is more or less, I would say that the rigorous mathematical proof is like that, but you also you need to consider the multi-graphs as well, and considering loops and considering multi-edges. But you can immediately convince yourself that this is actually correct. Okay, so this is a very important rule. So connected, planar, but simple or multi-graph. So this is always correct. Okay, now let us describe a new concept here. Degree of a region. So far, I have only explained you what is the meaning of degree of a vertex in a graph. And that was the number of edges emitting out from that vertex. Yes, and in that counting, if you remember, the convention was that whenever a loop happens, a loop contributes 2 units to the degree of that vertex. Yes, do you remember that? Okay, now this is a very nice idea. Mathematicians realized that it would be good if we talk about the degree of a region in a planar graph. But of course, the degree of a vertex is always is a is a that is a concept which is defined for all possible graphs, but here the degree of a region, because the notion of region in the first place makes sense only for planar graphs. So when we talk about the degree of a region, definitely we should talk about planar graphs, not in general. Okay, let R be a region of a planar graph embedded in the plane. The number of edges on the boundary of R is called the degree of R. So the number of edges that actually you see on the boundary. And it is denoted by degree of this capital R. By definition, there is another convention like the degree of a loop. An edge connected to a leaf is counted twice in the degree of the region, including that edge. Okay, so this is analog of the loop here. So let us understand this concept here. Consider the following graph. Determine the degree of all regions, and then this is interesting pattern, and then find the sum of all these degrees. Okay, so determine the degree of all edges, all regions. First of all, let us concentrate on finding the regions. This is the graph that we had in the previous session. So there is one region here, do you agree? And then there is another region here, number 2. For example, here number 3, here number 4, here number 5, and here number 6. Is there anyone? Is there anything more? Outside, 7. So there are 7 regions for this graph. Agree? And now what we do is this. Let me do this one by one. So when we say degree of the region number 1, I mean go to this and count the number of edges which actually restrict that region, or count the number of edges on the boundary of that region. So this is the region, and then how many edges you see for the boundary of that region? There is only one edge, and that is the loop. Yes, so I would say the degree of region 1 is defined to be 1. Yes. Okay, so now can you tell me what is the degree of R2? R2 is here, you see. This is your R2. So how many edges you see in the boundary? 2. One is coming from this part of the loop, and one is coming from this part of the loop, yes? So it means the degree of this region is 2. And I think some of them are very clear. So degree of R3, what's that? It's also 2. Degree of R4, it's 3. Degree of R5 is 2. Degree of R6 is 1. And this is a little bit, you need to be careful. So degree of R7. So it is actually, you need to count them. So I start from here, for example. So outside everything is we consider as the region 7. So this is one of the edges in the boundary of 7. Yes, this is the second one. This is the third one. Yes, this is the fourth one, and this is the fifth one, and when we are done. So is that understandable? So this is the number of edges that we face when we are dealing with region 7. So how many was there? 1, 2, 3, yes, 1, 2, 3, 4, 5, yes? So this 5. Okay, so as simple as that, yes?
Is there a convention for naming the region itself?
No, I haven't seen any conventions. Okay, so now let us add these numbers, because here I have asked, then find the sum of all these degrees. So it means that I am interested in calculating the sum of degree of R sub I. I goes from how many regions? 1 to 7. If I add them, it becomes 1 plus 2 plus 2 plus 2 plus 3 plus 1 plus 5. Yes? If I add them, it becomes 9 and 15 and 16. Yes, am I right? Okay. Let us see what is the pattern here. So what is this 16, do you think, in this graph? It shouldn't be hard. So let me change my color here and tell you what's going on. So when you are calculating the degree of this region, you are counting this loop once. Is that understandable? So let me put this here. So it means that I counted this once when I was counting the number, when I was calculating or determining the degree of R1. But when I go to R2, what is happening? So you see the degree of R2 is 2. Where this 2 is coming from? It's coming from the number of edges on the boundary. So it means that if I take my pen, it means that I count this once, yes? I also count this again, yes? Because when I say 2, I am counting this loop again and this loop as a new one. Do you agree? Okay, let us go to, for example, R3. So when I go to R3, what happens? I am counting this edge and I am counting this edge for the boundary of R3. Yes? When I go to R4, what I am counting this again for R4. Yes? I am counting this once and I am counting this once for R4. But when I go to R5, again I count this once more. Yes? But I also count this once. Yes? When I go to R6, I am counting this once. Agree? But now let us go to R7. When I go to R7, do you remember I started from here? Yes? I started from here. So in R7, I'm counting this once more. Yes? And I am counting this loop, bigger loop once more. I'm counting this once more. And I'm counting this once more. And I'm counting this once more. Yes? Now what is happening? You see on each one of the edges how many dashes you see, how many marks you see? 2. Yes? So it means that if I start adding all these degrees together, I am counting each edge 2 times. So it is clear, what is this number 16? 2q, yes? And this is exactly clear in this picture. So this becomes 2q. Is that understandable? So it's a very simple notion, and it becomes important in a few minutes. Okay, so let us do this for this graph. Okay, so if you don't mind, let me pause the video, and I want you to do this. By the way, so let me just explain this. There are two graphs, G1 and G2. You see, are these two graphs isomorphic or not? Yes? They're isomorphic, yes? What I have done, instead of drawing, so everything is more or less, everything is the same. That's a copy paste. But this one, this edge in the first quadrilateral is inside, and then I have done the other edge outside, yes? So here you see this edge, instead of drawing it inside, I have drawn it here, okay? So these two graphs, by the way, do you agree that these graphs are planar embedding of some graph? Yeah, they are planar, yes? Okay, so now I want you to do the same question for G1 and G2. So I want you to determine the degree of each region in G1 and the degree of each region in G2 and find the sum of all these degrees, okay? And then can you see the pattern? Of course, you already discovered the pattern. I will pause this video now. Okay, so now let us go back and see. Could you find that, for example, first of all, do you think that the number of regions here and the number of regions should in principle be different? No, because if that's the case, the notion of region doesn't make sense at all. I told you that we didn't prove this, but if we have two different ways of representing the same planar graph, if in one of them region is 5 and the other one region is 6, then the notion of region doesn't make sense at all, yes? So definitely the number of regions are different, but you see that if I draw it differently, it will affect the degree of the regions, not the number of the regions. Is that understandable? Yes. So the degree of region 1 might be a little bit different from the degree of region R1 here. Of course, it is clear that there is a leaf inside. But overall, it will not affect the sum. the sum will remain exactly equal to 2q again. Okay, so let us check. For graph number for G1, so how many regions you see? Do you agree this is one region? Yes. And then this is the second region. And this is the third region. What is the other region? Everything outside, yes? So there is only one more, 4. So if I say where is 4, you would say that all these things, yes, all of these are actually 4. Yes? So now if I ask you, this is important, if I ask you what is the degree of R1, what is your answer? You need to bring the convention in. So what's the degree of R1? It's 6. So it's reasonable, by the way. This is the regions, yes? I come here, 2, 3, 4, 5, and then I go back again here, more or less, 6. That's the region, yes? Is that understandable? So this is why a leaf is counted 2 times. It's natural because it seems that you're going around the leaf, yes? So there is this degree of R1 is 6. Degree of R2 is, it's clear, 3. Degree of R3 is 5. Agree? But let us count the degree of R4. So the degree of 4, you need to start from somewhere. For example, here, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, let me see. Yes, I have to go. There's no way. 10, 11, 12, yes, 13, 14. Yes, it seems to be 14. Am I right? So what did you get? Let me redo it again. And it doesn't matter now where you start from. So for example, let us start from here this time. So this becomes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yes? So it doesn't matter how you count it. So it is 14. So you see that here you're also counting this edge 2 times. Yes? And now let us add these numbers. So the sum degree of Ri, I goes from 1 to 4. How much is that? 28. Yes? And let us count how many edges we have. So what is Q in this problem? So 4 here, 5, 6, 7, 8, 9, and 5 here, 14. Yes? So you see that this is equal to 2Q. Yes? And now let us go the other one, G2. So what is G2 here? How many regions you see? 1 region, 2, 3, and 4. So the number of regions is not changed. This is problematic. If it is supposed to change, then we would be in trouble. Yes? Okay, but let us see what is degree of R1 this time. So what is degree of R1? It's clear. Is 4. What is degree of R2? It's 3. What is the degree of R3? What is that? It is 5. And let us consider the degree of R4. And you will start from somewhere. For example, here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Yes? So it becomes 16 this time. If I add them now, so sigma degree of Ri, I goes from 1 to 4. So how much is that? 21, 24, 28. And again, if I ask you what's Q, of course it is clear that it's 14 still, and that's exactly equal to 2Q. So is that understandable? And then, by the way, you can also check the Euler's formula. So what is P minus Q plus R here? So how many vertices are there? So 1, 2, 3. So how many vertices are here? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes? So P is 12 minus 14. What was R? R was 4. So if I calculate that, it becomes exactly 2. And if I do the same thing here, of course, nothing is changing. Yes, what is P? P is exactly 12. Q is exactly 14. And the regions are still 4. So that is also 2. Yes? Okay, so here, this is exactly what I want you to understand. So if you have a planar, simple, or multi-graph, and then in any planar embedding of G, we have this relation, so which we actually discovered. And the proof is not hard, actually. Every region, any edge on the boundary of any region is counted 2 times, yes, when you add all these degrees together. Okay, so now let us go to this very nice idea. Do you remember I told you that there are 2 simple examples of non-planar graphs? Do you remember? I told you remember them. One of them is K5, and what was the other one? Do you remember? So what is K5? Do you remember? I told you that this is the word is complete graph, and I don't know, for some reason they show it with capital K, not with C. So a complete graph is a simple graph that every 2 vertices are connected. So this is the full graph, if you want to say it full. Every vertex is a full vertex, yes? And now when I say K5, it means that I have 5 vertices. So this is one of the most simplest, most famous non-planar graphs. So if you remember, this graph is something like that. So let me see if I can draw and hold. So let me close this feature now here. So here we go to draw this. Yes, and then you have this. Every 2 vertices should be connected, actually. Sometimes these features are not working fine. Let me just draw it with hand. Okay, so this is K5. We want to claim that, we want to prove that this cannot be planar. Yes? So remember this as an example in your mind if you are interested in graph theory. So K5 is probably one of the simplest graphs that you cannot draw it without, we cannot have a planar embedding of that. So you might say that, okay, I can redraw this picture in a way that I do not have these intersections anywhere. But we want to show that, no, this cannot happen. Okay? How do you think we need to reason that? It's very hard. Usually these kinds of questions are very hard. We want to show that don't try hard. You will never ever succeed to draw something that you do not have these intersection points on which they are not vertices. So let us first of all, this is a simple graph and it is connected graph. We say that if, but we prove by contradiction. Let us assume that this is not the case. And K5, which is a simple connected graph, is planar. Yes? Then, by Euler's theorem, what should we have? We should have P minus Q plus R is equal to 2. Yes? Where R is the number of regions of any planar embedding of K5. Is that understandable? I want to show that no, K5 is non-planar. If you say no, it is not the case, it means that you have to admit that K5 is planar. On the other hand, we see that K5 is simple and we see that K5 is connected. So K5 is simple, it is connected. By this assumption, it is also planar, so Euler's theorem is applicable. So it means P minus Q plus R should be 2. If someone asks you what is P, you just count the vertices, it is 5. If someone asks you what is Q, you can count the edges and you see that this is 10. And then what is R? R is the number of regions of any planar embedding of K5 because you are claiming that K5 is planar. Okay, if I put these by Euler's formula, then what happens? This implies that 5 minus 10 plus 2 plus R is equal to 2. So what do I get for R? R becomes 7. Yes? So what I get for R is 7. But on the other hand, I know that the sum of all the degree of regions I goes from 1 to 7 should be 2 times Q. Yes? But what is 2Q? It is 20. So it means that sigma I goes from 1 to 7, the degree of all regions is equal to 20. Do you agree? But now tell me, there is a limit for each degree of regions. Can you tell me in this simple graph, what is this graph is loop-free, is not multi-graph. So can you tell me what is the degree of each region at least? Assume that you have a graph which is not a multi-graph, which is loop-free, and you want to see any region. What is the minimum number of edges limiting, what do you say, how do you say? Uh, I don't know, how many the number of edges around that region, at least? It's 3. Agree? So this is definitely greater than or equal to 3 for all the regions because it is a simple graph without loop, without multi-edges. But then you see it's a contradiction. Do you agree? Because you see that the minimum of each one of these numbers is 3. How many numbers are there in total? 7. 7 times 3 is 21. So the minimum value of the left-hand side is 21. On the other hand, we have to admit that the sum in total is 20. Is that understandable? And that's a contradiction. It's a very, very nice and simple. So might be you couldn't, if you want to, by the way, really think about this problem. Assume, put yourself in a position that you want to solve this problem from scratch. It's a very wild problem, yes, because you have infinitely many degrees of freedom to think about it. But this very simple argument, it's a very elegant argument, tells you that don't try hard. You will never ever find a planar embedding for K5. And that's one of the most famous non-planar graphs, K5. So, okay. So I would say that, therefore, this implies that the sigma degree of Ri, I from 1 to 7, is greater than or equal to 21. But this one and that one, contradiction. Yes? Is that understandable? So we see, let me just review it. It's abstract a little bit. We say that we want to show that K5 is non-planar. Yes? If you say no, it means that you admit that K5 is planar. Okay? And we see the graph is a simple graph and connected graph. So it means K5 is not only planar now, it is also connected and simple. So it means the Euler's theorem is applicable. So it means that I can write this formula. Yes, but P is easy. I just count the number of vertices. Q is easy. I just count the number of edges and put them in the Euler formula and solve this very simple equation and find R is equal to 7. it means that it doesn't matter how you draw it, there should be 7 regions there. Yes? And then what you do, you use this theorem, and instead of Q you put 10, you get 20. But I am asking you, think, if you have a region in a planar and simple graph, the degree of each region is at least 3, because if you want to make a degree 1, it means that you should have a loop, but our graph is simple, so it's loop free. And if you want to have a degree 2 for your region, it means that you have this situation. So, and this is also forbidden here because that's a multi-edge, but I am not allowed to have multi-edges. Yes? So it means that the minimum degree of each region is 3. And I have 7 of them. So the left-hand side should at least be 21. On the other hand, based on the previous theorem, the sum should be 20. And this is a contradiction. Is that understandable? So K5, remember it in your memory if you're interested in graph theory. K5 is one of the building blocks of non-planar graphs. And if you remember, I mentioned it in the previous session, there is another famous one, and that is K33. And that is called complete bipartite graph. Do you remember? We put 3 points top, 3 points below, and then we connect each point on top row to each point in the bottom row, but not between themselves. Yes? So now we want to show, if you remember, these are two famous non-planar graphs. We want to more or less understand why the bipartite graph K33 is non-planar. The idea is more or less similar, but you need to think a little bit better. Okay, so let me not spend so much time. Let us do it quickly. So let me just draw K33. Do you remember? So I put 3 points here, and I put 3 points here. So I connect this point to that, this point to this, yes, and then this one to that one. Okay, let us understand why this is non-planar again. So this is K33. So I don't want to repeat these. So you need to write everything like that. Let us assume that this is not the case, and K33 is, which is simple connected graph, is planar. So it means that I can use Euler's theorem and write this, okay? P minus Q, proof by contradiction. Let me just write it here. Okay, so here, what is P in this problem? It is 6, yes? What is Q, by the way? Q? Isn't it 9? So Q is 9, yes? And then if I put it in the Euler's formula, if you say that it is planar, it means that Euler's theorem is applicable. And then this should be 2. P is 6, Q is 9, R is left for me, is equal to 2. And then what I can conclude, R is how much? 5. Do you agree? Yes? But the point is that, of course, it is still true. So let me write this sigma. Sigma degree of Ri, I goes from 1 to how many? 5, is equal to 2Q. So it becomes sigma I goes from 1 to R. So let me write R here. But R is 5 now. Degree Ri. 2 times Q, what is? It's 18. Yes? But you see, the previous method does not give rise to contradiction. Because if I write the degree of R is at least 3, which is of course true, what happens for the sum on the left-hand side? It would be at least 15. Yes? This tells me that the number on the left-hand side is at least 15. This tells me that this number is 18. There is no contradiction. Do you understand? So if I want, so I need to be a little bit wiser. Can I restrict the degree for this particular case a little bit more? So do you understand what I mean? If I want to follow exactly what I did in the previous case, I will be in limbo situation. I don't have the proof, I don't have the contradiction. because there is nothing contradictory here. The left-hand side is at least 15, and this tells me that this left-hand side is 18. No contradiction. But the point is that for this particular case, can I write something better than the degree of r is? Yes?
It should be at least 4.
Yeah, it is at least 4 in this case. Yes, do you agree? In this case, the degree is at least 4, because if you want to have a degree, if you want to have a region with degree 3, it means that you should have a triangle somewhere in this. There are no triangles here, because triangles means that you should have an edge here horizontally, but you don't have any edge horizontally by the definition of K sub 3, 3. Yes? Is that understandable? Okay, so that's exactly the case. So at least you understand that these things looks very horrible, but if you see that there are very simple, elegant proofs for them. So here in this case, we will say that the degree of Ri in this particular case is at least 4. Okay, so this means that sigma I from 1 to 5 degree Ri should be, for this particular case, at least 20. And then you see that it's contradiction. Yes? Is that understandable? Okay, so remember, these are two famous graphs, and in the a little bit more advanced theory, whenever you want to see if a graph is planar or not, you will try to recognize one of these graphs inside your complicated graph. If one part of that graph includes this is called a subgraph. If a subgraph of a complicated graph includes either K sub 3, 3 or K sub 5, then it means the whole graph will be non-planar. Because if one part of the graph is non-planar, do you agree with me? The complicated graph definitely will be non-planar. So this is one way to understand that if the more complicated, but of course, this is easier said than done, because by looking at the complicated graph, if you want to see that pattern, it's not that easy, but might be you can write in a code so that you can recognize that. Any questions? Okay, so this is something I want you to know. And now we reach to this very famous and ancient problem, actually. So there are some definitions I want to give it to you here to present it for you. And that is the notion of polyhedron. Okay, I'm making mistakes. So, okay, that's correct. Regular polyhedron and Platonic solids. So a polyhedron, plural form is polyhedra, is a solid object in 3 dimensions that is bounded by flat surfaces, okay, like rectangle, for example, or I don't know, pyramids, prisms. Yes. Okay, a polyhedron whose faces are all the same regular polygons is called a regular polyhedron or Platonic solid. Not solids. Platonic solid, okay? Platonic, or what is the pronunciation, by the way? So because the name comes from the name of Plato, yes? Let me... Platonic. Okay, Platonic is the good pronunciation. Platonic. Okay, so every polyhedron corresponds to a planar graph. Okay, so you need to convince yourself a little bit about this. And I will try to give you some demonstrations on GeoGebra to see this a little bit more in practice. So faces of the polyhedron correspond to the regions of the corresponding planar graph. So this is a solid object. I don't know how to teach this part. I want to rely on your intuition. So do you see that this is a polyhedron by definition? Yes, because a polyhedron is a solid object. You see a solid object here that is bounded by flat surfaces. So these are flat surfaces. And then I am claiming that I want to convince yourself that to every polyhedron, I can associate a planar graph. And it is not hard to visualize it. Of course, it's still for simple solids. I don't know how to teach you. For example, assume that this is a rubber, this is a elastic material, and then you can press it from above to the ground and just smash it, I don't know, on the layer of the ground. Can you imagine what will happen for the graph? Keeping the red lines. The red lines are actually, I don't know, you can consider them rubber band, so they can increase the length. Okay, so you are pressing this, I don't know, can you draw something for what happens? Or you can see that, you can see it from above. Okay, but if you see it from above, it's not exactly correct, because if you really see it from above and do not stretch it at all, you will not be able to see these lines. Yes, you will not be able to see these lines. Mike, how do you see it? If assume that you just seeing it from above, do you agree that this would be a rectangle somehow with some line on it? Yes, if you see it from above. But now I want you to broaden your point of view. Not only see it from above, but I don't know. So I don't know how to show it. Take your hands here, stretch it a little bit, okay, and then see it from above. Okay? That graph would be the graph of the planar graph associated with that. I don't know. Do you want to draw it something like that for yourself? Yeah, you can start drawing it. I also try to imagine myself to see how this will go. My point is to draw this one on this side. So I don't know. I draw something here. Hopefully you agree with me. I'm not saying that this is the best one, of course. Yes. And then I will have something similar here on this side. Yeah, this should be completely symmetric, but I don't know, is that understandable for you? So I have so here what you see is actually this part. And there is something similar in on the back side, so that is this one. And hopefully you agree that then this line, so which line? This line, for example, is this line. And this line is this line. This line is that line. And this bigger line is this one. Yes, is that understandable somehow? So if I ask you what do you see now, you see that you see a planar graph if these are vertices. Yes, is that understandable somehow? You need to be a little bit artistic to understand what's going on. But this is more or less for this simple case. I don't think it should be hard to visualize that. Okay, and now let me ask you one question. How many regions you see here in this graph? How many regions? This is a planar graph, yes? Understandable? Is it planar? It is planar. But how many regions you see? So for example, 1, 2, 3, 4, 5, and 6. So how many regions you see? 6. One more, 7. Yes, outside. Okay. And then how many faces you have in your polyhedron before smashing it to the ground? Yes? It should be 7 if I am right. Yes?
Oh yeah, the bottom also.
The bottom also, yes? So how many faces you see in this solid object? Exactly, it is equal to the number of regions that you get in the associated planar graph to the solid object. Is that understandable? So if you have a solid object, to that solid object, to that polyhedron, not solid object, the polyhedron, by smashing it onto the ground or stretching it around as you like, you get a planar graph. You need to understand that the number of regions for this planar graph is exactly equal to the number of faces in the original solid, yes, object that you have. Is that understandable? But there is very interesting thing. There are exactly 5 platonic solids. Yes, so it's very important to understand this. So you cannot have more than 5 type of regular polyhedra. Yes. So let me, before doing this, this is the statement in the book. You might think that the proof is very complicated. Actually, the proof is not that complicated. So Euler actually discovered a lot of things in his life. This is one of them. Okay, so let me just show the picture for you here. So these are famous 5 Platonic solids. We cannot have more than them, and that's a theorem. Yes. So here it's a cube here, a cube. The faces are squares. So what is the meaning of regular polyhedron? Be careful to understand the theorem. It means that the faces should be regular polygons. Yes. If I ask you what is the regular polygon here, you would say every face here is a square. A square is a regular fourth quadrilateral. Yes, this is one of them. And here, this one is called tetrahedron. So what is the regular polygon involved here? It's an equilateral triangle. Yes, all the faces are equilateral triangles. Is that understandable? Yes. And the name of this probably might be these two, you knew about them, but I don't know, do you know the name for this one? Have you seen this in the movies, or if in action? Have you seen these pyramids in Egypt? So if you put 2 of them, connect, attach them like this is called octahedron. Octahedron. Yes, and this is called if every face is a pentagon, a regular pentagon, then this is called dodecahedron. And finally, again, you have triangles involved. You see, in 3 of them, equilateral triangles are involved. In cube, squares are involved, and in dodecahedron, actually pentagon is involved. Yes? So then you will have, this is called icosahedron. Yes, so we can have only 5 regular polyhedra, and these are the names: cube, tetrahedron, octahedron, dodecahedron, and icosahedron. Yes, so these are the only 5 objects that we can have. But let me show you another picture here. Don't get confused. These are also polyhedra. Why that is not a contradiction here? So there are nice pictures. You can see that all of them are solid objects. So these are polyhedra. Why? Because each face is a flat face, is a flat polygon. Why this is not a contradiction, even though we have a lot of them here in this picture at least? Yes?
Because the types of faces are mixed.
So they are not regular. So this claim in this theorem is only for regular polyhedra. If you want to have the same polygon for each face, regular polygon, the same type for each face, then there are only 5 options. And these are the only 5 options, okay? You see, in each case, all of them are pentagons here, yes? All of them are pentagons here. They are regular. All of them here are triangles. All of them are here triangles. But here, when I go to this picture, when I go to this picture, for example, concentrate here. One of them is a square. The other one is a triangle. So this is also a solid object. That's also a polyhedron. But this is not a regular polyhedron. Is that understandable? Okay, so might be before doing the proof, I want to show you some demonstrations here to see if it works. Let me see, if I have already prepared them, it works. So let us go here, make it bigger. So it's a little bit hard to see. This is octahedron. Do you see I want to give you a little bit of time to realize that's octahedron. So there is a square here. So let me show it here. I cannot show it on with pen. So there is a square here, and then you have a pyramid on top and a pyramid below. They are connected from the bottom. Yes. So that is the octahedron. And then, do you agree that if I just draw this graph, so what you see on this picture is the graph connected to octahedron, associated with the octahedron. Do you agree? Yes? So I am just putting a point for each vertex of the octahedron, and I am drawing a line between any two vertices which are in reality connected with the edge of with an edge. Is that understandable? Yes or no? Okay, so now let us get rid of that. In the books, you see the right-hand side picture as the octahedron graph. Yes? In this way, do you see, if I bring it back, so I hope that you agree the graph on the left-hand side is exactly the octahedron. Yes? But when I take it off and you don't see the octahedron, you see something which is not a planar embedding. Is that understandable? It's not a planar embedding because we have intersections at these points, which are not vertices. But you can draw it, you can redraw this in this form. Yes? But do you agree if I can redraw the left-hand side graph as the right-hand side graph, it shows that this is a planar graph. Yes? Okay, how can we do that? I don't know. You need to play a little bit of game. Do you? Because you can move them around. Okay, so do you do you see that? How can I do that? Pardon?
The one below the one you just moved.
So if you just move this one here?
Yeah, up more.
No, but the point is that I want to make it try. Okay, up here, you mean?
Yeah.
Okay, and then
Then the corners, the bottom should be moved, like stretched out.
how much? Here?
More. Yeah. And then the same thing with the other.
But there is no space here.
Yeah, but
Okay, so let us bring this down. Okay. Okay, so we want to find a triangle outside. I don't know if we can play, how much we can play this game. I should have trained myself before doing the lecture, but anyway. So, if you don't mind, let us do the same thing because I want to make this my triangle. Okay, so then what should I do? I need to bring this in and I need to bring this in. Okay, it was simpler. Yes? Yeah. So now you see it's working. I hope that you agree this is working. So it means that if I so let us go back here. Yeah, we cannot go back probably. Yeah. So I started from a octahedron. I drew on a graph exactly on the octahedron, and I make the octahedron disappeared. I got something which was the same graph, but it was not a planar embedding of that graph. What I was claiming in that remark is that for every regular polyhedron, you can associate a planar graph. And that is exactly what you see in this demonstration. Is that understandable? Yes or no? Okay, but might be this puzzle becomes harder. Let us see if we can have a little bit of more challenge. So here, let me go back and then what should I do now? Okay, so let us go to the other one. This is more challenging. So do you remember we talked about the graph on the right-hand side, and I named it dodecahedron graph. Do you remember in which context we talked about that graph? In which context? Hamiltonian. Yes, we showed that this graph on the right-hand side is a Hamiltonian graph by finding a Hamiltonian cycle there. And this is a dodecahedron, okay? I hope that you agree with me that that's a dodecahedron. For example, this vertex is this vertex on top. This vertex that you see is the vertex which is below the picture. Yes. So if you see this on the left-hand side, you see the dodecahedron, and then I have associated a point with every vertex and a line with every edge. And now let us make this disappear. We will see this graph. And this graph is actually not planar in this way, at least. Yes, I should be able to convince myself that this graph, by playing around, can be turned into the graph on the right-hand side. And this means that for dodecahedron, we can actually have the planar embedding. Okay, I don't know. So do you want to come and play around to see if you can draw it? The idea is what I am seeing. The way that I think is that I see a regular pentagon outside. I will try to detect a pentagon somewhere here and stretch it out, and then it might be helpful that I can, for example, can you see a pentagon here? Where is that pentagon? So this is a hexagon. One. Yes, exactly here. Yes. So here, let us try. I don't know if we can do it here on iPad, but let me stretch that one out. So I will take this one out so we shouldn't get confused. Be careful. Help me to do that. Okay, so that was this one, and I have to pull this one out, and this one out, and this one out. Do you agree? So so it is 5. So let me make it nicer a little bit so that it helps us to understand what's going on. So unfortunately, we can go here. Yes, that's good. Yes, do you agree with me? It's more or less a pentagon outside. Yes? Oh, at least we are done. Yes, because I was I was claiming that we can draw a planar one. Yes, do you agree this is a planar one now? Because the intersections are only happening there. But this is actually already done. Yes, because if you want to make it nicer, how should we do that to make it nicer? So I think every one of you agreed that this is exactly the same graph. I need to play around a little bit. So for example, make it a little bit smaller here. Uh, Something like that. And I don't know, for example, this one, I can make it a little bit longer and then make it closer here. Yes, and make it closer. I hope that I could convince you that they are the same. Yes? So you realize that this is the reason that we call this dodecahedron, because the reason it's coming from the dodecahedron. So apparently, I don't know if we can prove them rigorously here or not, but of course there should be something in the rigorous proof. And let us go to the next one. Might be this is the hardest one. Icosahedron is probably the hardest one. Uh, so that is an icosahedron, yes? And then exactly the same scenario. If I let it disappear, then I will be left with this, okay? And then of course this is not in this form. It doesn't look planar. I don't know why that's the blue point there. But anyway, do you have any idea what we can do here now? Again, the idea is that this is my experience. Let us think about a triangle that we can pull it out. Yes, Carl?
The triangle.
Yeah, here. Let us pull it out. Yes. So let us pull this triangle out. Oops, this doesn't move here. How? Yeah, this doesn't go around here. I don't know. Okay, so because I want to put everything inside, might be that's not enough space here. Okay, so do you mind? Let me just bring everything inside here. At least. Okay. Now it seems right, yes? Do you agree? This one is this should be the triangle in the middle, because I have also a triangle, inverted triangle here. And then yes, that's exactly the same picture. Do you agree with me? Yes. Yeah. Do you agree that they are the same? So these graphs are famous graphs. If you see them somewhere, you should remind yourself. So if someone asks you what is the connection between this graph and icosahedron, now you understand the connection. Yes? Is that clear? And then on this, on these notes, I have given you these addresses that if you want to play around yourself, we will see how it works. But let us go back to see why this is indeed the case. This is given in the book, but somehow in the part that you're supposed to study for yourself. Okay, so you might think the proof for this idea is very hard, but it is not that hard at all. Okay, so why do you think there should be exactly 5 Platonic solids? So it was, by the way, you see, this is an application of graph theory in just pure geometry. Yes, we are using very rough ideas in discrete mathematics to actually prove that this is indeed the case. Yes?
Is it the only way that we can repeat the shape without violating the p minus q plus 2 equals r?
Equals to 2?
Yeah, equals to 2,
Yeah, so let us, yeah, exactly. But we want to elaborate more. So you see, this understand. So let us assume that you have a regular polyhedron in your hand, okay? And then you associate, but based on what you learned here, I hope that I could convince you at least partially that for each one of these polyhedron, you can associate a planar graph. Yes. So let us consider it like this. P. Let us consider this P, the irregular polyhedron. Okay. And let us from here. Let me consider a associated graph is G. Let us consider G is the associated graph to this corresponding planar graph. Okay, so let us consider the characteristics of this planar graph. So let us consider P is the number of vertices in this planar graph, and let us consider Q to be the number of edges in this planar graph, and let us consider that R be the number of regions of this planar graph. Yes. So these are, I'm assuming that these numbers are characteristics of this corresponding planar graph. We know that P minus Q plus R should be 2. Why is that? Because this planar graph is connected, is planar, and it's simple. So it should follow this rule. But we can say more than that. Do you think that, what can I say about the degree of each vertex? Yes, do you want to say something?
This, I think, shouldn't the degree of every region be the same?
Be the same. Exactly. Is that understandable? I don't know what that degree is, but the degree should be the same. Yes. So I would say that let M be the degree, be the same degree of all vertices. Okay, but can you tell me what is the minimum value for M? Can I have a degree 1 vertex? So what's the minimum? It's 3, yes? So the minimum value is 3. It cannot be lower than 3, yes? Another thing that I want you to understand is that, do you think the degree of regions should also be the same? The degree of regions should also be the same because they are actually, somehow they are the projection of the same polygon. Yes? So the number of, so the degree, so let n be the same degree. Of course, here there is a question mark here, but we answered this orally. So let n be the same degree of all regions. Again, can you see any limitation for n? N cannot be smaller than which number? It should start at, what is the minimum value for n? It's also 3, yes. Okay, so now it's very, very simple, by the way. The degree of all the vertices I goes from 1 to p is equal to 2q. So what can I write for the left-hand side? Can you tell me? Because the degree of all vertices is equal to m, so the left-hand side becomes what? P times m equals to 2q. And from here, you can get p is equal to 2q over m. And we also learned today that sigma of all the degree of all regions I goes from 1 to r is again 2q. We just learned this one today. So, but on the other hand, the degree of all the regions are the same, and it is equal to n. So the left-hand side can be written as r times n is equal to 2q. Agree? And then what does it mean? It means that r is equal to 2q over n. Yes, is that everything understandable? Of course, we are adding some imagination into it as well, but all of them can be made very rigorous. Okay, but then we have p minus q plus r is equal to 2. So then this implies that instead of p, I put 2q over m. Instead of q, I put q. Instead of r, I put 2q over n. On the right-hand side, I have 2. And let me factor q over mn out. On the left, what is left for me is 2n. I will motivate you why. Of course, this is a simple algebra. So why what I have written here is valid. If you don't believe me, you just multiply this back. If you multiply this back, n and n are cancelled. 2 is multiplied by q, 2q over m, and that's 2q over m. And if you multiply this by the middle term, mn and mn are gone, so it becomes minus q, and that's minus q. And the same story, if I multiply this by the last one, m and m are cancelled, so you get 2q over n. Agree? But that's a very, by the way, crude reasoning. You don't need much here. You just want to convince yourself that is positive. Yes? Because that's the product of two numbers that's equal to 2. So it means that 2 is positive, so each one of them should be positive. This is already positive. Q is the number of edges, m and n are the number of degrees of vertices and regions. They cannot be negative. So this would then imply that 2n minus mn plus 2m is positive. Do you agree? And now you see this is a very simple algebra. You add minus 4 to both sides. Yes? And then you factor the left-hand side out. You factor the left-hand side. Let me double check it for you. I am claiming that the factorization of this is this. Why? Let us multiply. N times 2 is 2n. N times minus m is minus mn. Minus 2 times 2 is minus 4. Minus 2 times minus m is positive 2m. So what I have, so do you agree now that this one and this one are exactly the same? I just multiplied them back and showed. Now then the final step is to multiply both sides by a negative sign. I keep the first factor the same. I multiply the negative sign here. Then it becomes m minus 2. And because I am multiplying by a negative sign, I have to change the sign, and the right-hand side becomes 4. It's a simple algebra. You see, it's highly simple algebra at the level of Math 1C. If you're a good student in Math 1C, you understand the algebra here. Is that clear? But you just told me yourself that the minimum value for m is 3, the minimum value of n is 3, and then this product is supposed to be strictly smaller than 4. So there are not many options available. Yes, this is a natural number. This is a natural number, but the product of the two natural numbers is supposed to be smaller than 4. So what are the alternatives? One way is to have n minus 2 equals to m minus 2 is equal to 1. If this happens, the product is smaller than 4. Another scenario is what? N minus 2 is what? Is 3, and m minus 2 is 1. This can also happen. Yes? Another scenario is that n minus 2 is 1 and m minus 2 is 3. And is there any other option available? Can you see? There should be two more. And that's clear. N minus 1 is 1. N minus 2 is 2. N minus 2 is 2. M minus 2 is 1. Do you agree that these are the only possibilities if I want to have this product smaller than 4? Because m is greater than or equal to 3, this is a natural number. That's also a natural number. The product of two natural numbers is supposed to be smaller than 4. There are not that many cases. I have written, it might happen, this is 1, this is 1, this is one scenario. This is 1, this is 3, this is one scenario. This is 3, this is 1, this is another one. This is 1, this is 2, this is 2, this is 1. Can you see any other points? No. These are the only options. And how many options are there? 1, 2, 3, 4, 5, corresponding to exactly 5 platonic solids. So this is the reason that you can have only 5 type of planar graphs with these properties. And for each planar graph, we associate but of course, if you want to be careful, this is the other way around. This tells you that if you have a polyhedron, it should be one of these cases. So it means that this is a proof for saying that there are at most 5 of them. There cannot be more than that. Yes? But I hope that you can more or less, I couldn't convince myself why a dodecahedron can be made in the first place. For cube, it is easy. We can consider that we can make a cube. For tetrahedron, we can convince ourselves. For octahedron, that is easy. We have two pyramids, we put them on top of each other, so that becomes an octahedron. And for icosahedron and dodecahedron, you need to imagine why dodecahedron. So this doesn't tell you dodecahedron exists. This tells you that dodecahedron is one of my possibilities. We don't know if this is true, if this can be realized. So you need to think why dodecahedron can be realized and why icosahedron can be realized. This guarantees that more than that you cannot expect. Okay? Yeah, we need to think a little bit about that. So officially the graph theory will be finished here. Might be, Morten told me that if I need a class, so might be Wednesday I take that physics lesson from Morten and continue for the next chapter. Next chapter is also very good if you understand that. Okay, thank you very much.